Section 10.2, Rational Exponents. Rational exponents, in other words, exponents that are fractions. We understand what it means if I have something raised to an integer power. It means that thing times itself that number of times. This is 3 times 3 is 9. 4 to the third. 4 times 4 times 4, which we should have memorized, that is 64, and so on. So what could it mean if we have an exponent that is a fraction? If we have some number raised to, say, a 1/2 power. Now first notice I've written the fraction in slash notation, and this is typically how we will see our fractions written when they're exponents. Any other time we write fractions, we like to see them stacked. But when a fraction appears as an exponent, it's best and most readable if we use slash notation. So what could this mean if I raise something to the 1/2 power? Well, a few different ways to look at this. If I take some number a to the 1/2 and multiply it times itself, this is a product of like bases, so I can add the exponents. This gives me a to the 1/2 plus 1/2 is 1, a to the first, or simply a. Now, what else do we know that when multiplied times itself gives me a number? If something times itself gives me a number, then that something is what? The square root of that number. We know that square root of a times itself has to be a, because that's what a square root is. A square root is a thing that when multiplied times itself will give me the radicand back. Meaning that a to the 1/2 is the same as the square root of a. Another way to look at this, if I have a to the 1/2 times itself, that's the same as squaring. This is a power to a power. Power to a power you multiply. 1/2 times 2, half of 2 is 1. That's just a. And what else do we know? That a square and a square root undo each other. If I have square root of a and I square it, we know from the last section that just gives me a. So once again, a to the 1/2 is the same as the square root of a. 16 to the 1/2 power, that's going to be the square root of 16, which is going to give me simply 4. So a 1/2 power takes a square root. We could show a similar argument for higher denominators. If I have some number to the 1/3 and I multiply it times itself 3 times, add the exponents, that's going to be b to the first. So what does this b to the 1/3 have to be? This b to the 1/3 must be the cube root of b. So if I ask you, what is 8 to the 1/3 power? Well, that's just the cube root of 8, which is 2. In a brown box on page 662 here at the beginning of the section, it says the meaning of a to the 1 over n. And it says a to the 1 over n is the same as the nth root of a. A to the 1 over n is the same as the nth root of a. That's exactly what we did here at the top. That's nice so long as my numerator, my little numerator in my power, is a 1. What if that's not a 1? And a lot of what we do in this section is going to depend on our understanding of our rules of exponents from the beginning of chapter 4, sections 4.1 and 4.2. Let's say that I have 25 raised to the 3/2 power. Now, what does that mean? Well, I can think of it a couple different ways. I can think of this as 25 raised to the 1/2 raised to the 3rd. Not sure? Well, let's see if we get back. Power to a power, you multiply the powers. 1/2 times 3 is 3/2. I'm just unmultiplying those powers. And this means the square root of 25 being raised to the 3rd power. Another way I could interpret this is 25 cubed raised to the 1/2, which is the same as the square root of 25 cubed. So all 5 of these expressions represent the same thing. And when I'm working out a numerical problem, I'm typically going to choose this first path because it keeps my numbers smaller and easier to work with. Would you rather take the square root of 25 and then cube that? Or would you rather cube 25, get some enormous number, and then try to take its square root? I like this process better when we're dealing with numeric expressions. And we can finish this off. This will give me square root of 25 is 5, and 5 cubed is 125. The way I would probably show that from beginning to end, starting back at the original problem, is I'd say, well, this represents a square root of 25 being cubed, which is 5 cubed, which is 125. We'll get used to jumping right to this radical notation without having to go through this exponential notation on our way. Let's look at a few more brown boxes. On page 663 at the top, it says a to the m over n equals a to the 1 over n, all raised to the m. Now that's saying this right here. Our brown box at the top of 663 says that if I'm raising some base to a fraction, I can split that up as that base raised to 1 over the denominator, all raised to that little numerator. We have an equivalent brown box at the bottom of page 664. A to the m over n equals, once again, this is what we just looked at, a to the 1 over n to the m, or this one says I could also write a to the m to the 1 over n. And so this brown box includes this piece, where m, in my problem, m is 3 and n is 2. It goes on to say, as we've discovered, here at the top of page 665, that a to the m over n is equal to the nth root of a to the m. That's going to include this piece right here. Okay, the square root of 25 to the 3rd. Or it's also equal to this form, the nth root of a, all raised to the m. And so that includes that piece right there. So several brown boxes to get these 5 equivalent forms that we have here on the board. What I want you to remember is that when I have a base raised to a fraction, the little numerator is the power, the little denominator is the index. Look right here. 25 to the 3/2, the little numerator is the power, the little denominator is the index, and that's a square root, so we have an understood 2. So we're going to want to practice this. Let's jump to the homework and do several of these beginning problems. Number 12. The instructions will just read, evaluate. 121 to the 1/2. Raising something to the 1/2 is the same as taking the square root. And again, what we just said still works, doesn't it? The little numerator is the power. This is raised to the first power, which doesn't do anything, and we don't see it. And my little denominator is the index, this understood 2 in the square root. Square root of 121 is 11. Number 14. 512 to the 1/3. Well, a 1/3 power is just a cube root. We're talking about the cube root of 512. Again, that should be a memorized fact. Cube root of 512 is 8. Number 18. 8/27 raised to the 1/3 power. Well, that's just going to be the cube root of that base, that whole fraction, 8/27. And you remember earlier, last time we discovered that this just means the cube root of the top over the cube root of the bottom. Well, looking at it in terms of this rational exponent, doesn't that make sense? Couldn't I distribute that 1/3 to the top and the bottom and have 8 to the 1/3, which is just the cube root of 8, over 27 to the 1/3, which is just the cube root of 27. So yes, it does make perfect sense that the cube root of a fraction, or any root of a fraction, is just the root of the top over the root of the bottom, because radicals, it now makes sense, are going to behave a lot like exponents. Cube root of 8 is 2, cube root of 27 is 3. Number 20. Negative 32 raised to the 1/5 power. That simply means the 5th root of that base. The negative is part of the base, so the negative belongs to the radicand. 5th root of 32 is 2. So the 5th root of negative 32 is negative 2. Remember, with an odd index, we don't have that problem of taking the root of a negative not being real. It's an odd index, and so we can certainly do that. Number 22. Negative 36 to the 1/2. Negative 36 to the 1/2 just means the square root of that base. The base becomes the radicand, negative 36. And now this is an even indexed root of a negative. We know that that is not real. That is simply not a real number. But now I want you to compare this to this problem. Evaluate negative 36 to the 1/2. Is this different than the previous problem? We know it is, because in our problem from the book, the negative was part of the base of that exponent. In our new problem that we just made up, the negative is floating out front. What's the base? The base is just the 36. So this is our floating negative, and what? 36 to the 1/2. Square root of 36. My negative is floating out front, and the square root of 36 is 6. And so be careful with those parentheses. Let's look at number 30. Now we have a choice in interpreting this. We could interpret this, remember, your little numerator is your power, your little denominator is your index. So we could interpret this as the fifth root of negative 243 squared. Or we could interpret this as the fifth root of negative 243 all squared. Which do you think would be better for us in working out this numeric problem? I'd rather take that fifth root first and then square the result. It's going to be a lot easier than squaring a negative 243 and then trying to figure out what its fifth root is. So, as we work this, I'm going to put the power on the outside, use that interpretation, and write this as the fifth root of negative 243 all squared. Fifth root of negative 243, well, fifth root of 243, this is a memorized fact, right? That's going to be 3, but it's negative, so my 3 is negative, and that whole thing is being squared. Again, careful with the parentheses because we are squaring this negative. This is going to give me a positive 9. That negative is not floating. Before we look at the next problem, I want to consider one that's not in the book. Let me ask you to evaluate 49 to the negative 1/2 power. Now we think back to chapter 4. What does it mean when I raise something to a negative power? It means to take the reciprocal, or this belongs on the other side of the fraction bar. This base to its negative power, sitting in its own numerator, this sits over 1, right, is the same as 1 over this base to that positive power. So the first thing we'll do is interpret that negative exponent as meaning to reciprocate, to drag this factor across the fraction bar. 49 to the negative 1/2 in its own numerator is 49 to the positive 1/2 in the denominator. And now we keep going. We know that a 1/2 power is a square root, so that's a square root of 49 in our denominator, and we finally end up with 1/7. Now with that in mind, let's take a look at number 32. (27) to the negative 4/3 power. The first thing I want to do is deal with that negative exponent. We never actually raise something to a negative power. We interpret the negative power and then we crank it out. And a negative exponent means, hey, I belong on the other side of the fraction bar. So instead of sitting in its own numerator, this will be 1 over 27 to the positive 4/3. That's 1 over, the little numerator is my power, the little denominator is my index. So this will be the cube root of 27, and I'm going to interpret this as meaning all raised to the 4th. I don't want to raise 27 to the 4th power and then take the cube root. I'd rather take the cube root first and then raise to the 4th power. Cube root of 27 is 3, and 3 to the 4th is 81. All right, let's try number 36. Again, thinking back to the beginning of chapter 4 where we looked at our rules for exponents. When we have a fraction raised to a negative exponent, we know that all we have to do is flip that fraction over and it will change the sign on my exponent. And so this fraction to the negative 2/3 is the same as its reciprocal to the positive 2/3. We've interpreted the negative, now let's crank it out. Little numerator is your power, little denominator is your index. So this becomes a cube root of 125/64. And I'm going to interpret this again, putting that power on the outside so it happens last, all squared. Cube root of a fraction means cube root of the top over cube root of the bottom. Cube root of 125 is 5. Cube root of 64 is 4. We took the cube root. We still need to deal with our power of 2. We still need to square this. Square the top, square the bottom. All right. So there's some examples of cranking out these expressions. Now in the next bit of the homework, again, pay attention to those instructions. Pay attention to the instructions. All she wants me to do is write each exponential as a radical. And here she says, assume that all variables represent positive real numbers. That way we don't have to even worry about anything being not real. Number 40. All she wants us to do is write this exponential form in radical form. So change this over to radical notation. A 1/2 power is a square root. This is the square root of 3, and that's all she wants. That's all she wants. That would be an irrational number. It's approximately 1.732. But all she wants me to do is write it in radical form. Number 42. 7 to the 2/3 power. We have a couple different ways that we can write this. One way is as we've been doing it. Remember, your little numerator is your power, your little denominator is your index. This is the cube root of 7, and we could say that's all squared. And that's in radical form. There would also be nothing wrong with saying that this is the cube root of 7 squared. And stop right there, because all she wants is this to be in radical form. And either of these will work, especially since I don't need to go any further. Number 44. Now don't make these tougher than they need to be. Quantity 3p to the 3/4 plus quantity 4x to the 1/3. All we're doing is writing this in radical form. So if I have something to a fraction, the little numerator is the power, the little denominator is the index, and here we go. This is going to be, what, a 4th root of 3p all to the 3rd plus, separate term, a 1/3 power is just a cube root of that 4x. That's it. We've written it in radical form. We've changed it from exponential form to radical form, and that's all we've been asked to do. Number 46. Before we can jump to radical form, we've got to deal with that negative exponent. That negative exponent needs interpreted as meaning that this is 1 over that base, the whole 5y, to the positive 3/5. Now we can get on with our radical form. And so this will be 1 over, little numerator is your power, little denominator is your index. This is a 5th root of that whole 5y, and then that whole radical being raised to the 3rd power. And that's now in radical form. I want to compare this to a problem that's not in your book. What if I gave you this and asked you to write this expression in radical form? Change this exponential to a radical. Well, what's being raised to the negative 1/2 power? What's the base? Just the y. That 5 is floating out front. It's not in parentheses, and so it's not part of the base. It's not part of what is being raised to that negative 1/2 power. So when I go to take this across the fraction bar so I can change it from being negative to being positive, what goes with it? Just the y. The 5 stays where he is, because the 5 is not part of that base. The 5 is not participating as part of that exponential factor. And we'll drag the y across the fraction bar where it now becomes y to the positive 1/2. And to finish it off, y to the 1/2 is square root of y. And so we've written this in radical form. But notice we have to pay attention, as we've always had to pay attention, to what is the base, what's being affected by that power. Number 48. Again, don't make these harder than they need to be. First of all, don't make the unforgivable mistake and think you can distribute that power over addition, right? You cannot do that. You can distribute a power over multiplication or division, but you cannot distribute a power over addition or subtraction. All we've got to do is interpret this fractional exponent as a radical. What's the base? That whole thing in parentheses. So what's my radicand? That whole thing in parentheses. It no longer needs its parentheses. The radical sign is a grouping symbol. The little numerator is my power. The little denominator is my base. Is my index. So this is going to be what? A square root. I don't actually write the 2. I understand there's a 2 there. And that whole thing is being raised to the 3rd power. And that's that. Don't make the problems in that part of the homework tougher than it needs to be. All right. In this next batch, she says, write each radical as an exponential. So we're going the other direction. And she also says, simplify, if possible. And again, I'll assume all variables represent positive real numbers. Number 52. The square root of 5 to the 10th power. She says, now first, write this as an exponential. Okay? So a square root is a 1/2 power, right? A square root is a 1/2 power. So this is, we could take an intermediate step and say this is 5 to the 10th, and it's having its square root taken, so the whole thing is being raised to the 1/2 power. My parentheses and my 1/2 are replacing the square root sign. And then, power to a power, we multiply those powers. This is going to be 5 to the 10 halves, which is 5 to the 5th. Now, when we see a problem like this, most often we go straight to this step, because we know that that little power is going to be my little numerator and the index is going to be my little denominator. We're just going the opposite direction of what we did in the previous set of homework. She did say simplify, so we want to finish this off. 5 to the 5th power. Let's see, I know 5 to the 4th is 625. That's memorized, right? We just need one more factor of 5. So multiply, and that's going to be carry a 2 is 12, carry 1 is 31. Now, of course, I'm not going to give you numbers that big to crank out on a quiz or a test. I will certainly give you stuff that I expect you to have memorized from your handout of these powers should be memorized. But probably not something quite that big, although that is right on the cusp of what I would consider appropriate for a quiz or a test with no calculator. Let's do another one. Number 54. The fourth root of 6 to the 8th power. I'm going to skip that, what I called an intermediate step a moment ago, and I'm going to go directly to my 6 to a fraction form. This is going to be 6 raised to the, now my little fraction. The numerator comes from the power, the denominator comes from the index. This is 6 to the 8/4. You can always check it by taking it back that way. The little numerator is your power, that's right. The little denominator is your index, that's right. And 8/4 is 2. And 6 squared is 36. So nothing to it. Number 58. I like this problem. This is a good problem. This kind of problem tells me a lot about how well you understand this section. First, let's put everything in exponential form. And honestly, on a quiz or a test, my instructions would not give you any leading clues. It wouldn't say write each radical as an exponential. My instructions would say simplify. And you'll look at that and go, well, what in the world? Well, let me try putting them as exponents. Let me try writing this in exponential form and see if I get anywhere. That's what we're going to do. Fourth root of y is y to the 1/4. Fifth root of y squared is y to the, your power is your little numerator, your index is your little denominator, y to the 2/5. We said simplify. Are we done? Nope, this is a product of like bases. A product of like bases, you add the exponents. To add these exponents, we're going to need a common denominator. Least common denominator is 20. 1/4 becomes 5/20. 2/5 becomes 8/20. And then, adding the powers, we get y to the 13/20. And that's what you wanted me to do. That is simplified. I may ask you to simplify and add writing your answer in exponential form. That doesn't mean you cannot go through exponents. But at the end, you are going to want to change it back to the 20th root of y to the 13. Now that's only if I asked for you to write it in radical form. If I don't ask, well then right here we're simplified, we're done. Let's have a go at number 60. Fourth root of w cubed over sixth root of w. Well, if I'm going to get anywhere with this, whether she reminded me in the instructions or not, which she says, write these as exponentials and simplify, I know that one of the tools I have now is the ability to write radicals as exponentials. This numerator becomes w to the 3/4 over my denominator, w to the 1/6. Are we done? Nope, this is a quotient of like bases. I want to ask how many are left and where. to be able to make that comparison, to be able to subtract, I need common denominators. Least common here is 12. 3/4 becomes 9/12. 1/6 becomes 2/12. 9/12 W's in the top, 2/12 W's in the bottom. How many are left and where? 7/12 factors of W are left in that numerator. And if I were asked to write this back in radical form, if I'm not asked, I can leave it like this, or I can change it over to my radical form. Either way. And I believe that for these problems here, 58 and 60, she actually gives answers in radical form in the back. But either will do, because we were not told what form to leave our answer in, just that it was to be simplified. All right. Let's turn our attention to this next set of problems, which there's nothing new here. There's nothing new in this next batch in the homework. It's like we're back in chapter 4. Now, if you look here on page 666, our rules for rational exponents, well, these are the same as our rules for exponents. At the end of chapter 4, at the end of section 4.2, we had a large box that summarized all the rules for exponents that we had to that point. And that's all we're doing, is we are restating those rules. Saying what? What does this first one say? A to the R times A to the S equals A to the R plus S. Product of like bases, add the exponents. The next one says a negative, drag them across the fraction bar. Right here, quotient of like bases, subtract the exponents, or we like to say, how many are left and where. A fraction to a negative, you flip him over, and here she actually shows distributing the positive R after you're done flipping it over. This one, power to a power, you multiply the exponents. Here we see we can distribute a power over a product, distribute a power over a quotient, and so on. So these are the same rules of exponents that we had back in chapter 4. We're going to work some problems now, and the only difference between these problems and what we had in 4.1 and 4.2 is that our exponents are going to be number 62. And here she says, simplify each expression, write answers with only positive exponents, assume that all variables represent positive real numbers. I am not going to remind you to write your answers with positive exponents. We know that that's a rule of simplification. And it might even be worth taking a look back at chapter 4, the homework from section 4.2, and trying a couple of those to get warmed back up before starting in on these problems in this section of the homework. So here we have a product of like bases. A product of like bases, you add the exponents. This is going to be 6 to the 4/3 plus 2/3 is 6/3. 6/3 is 2. And this 6 raised to the second power is 36. And there's that one. Number 66. You may recall that in chapter 4 I would often say there are many ways to work this problem. On most of these I'm just going to show you what I think is the slickest way and be done with it. But on this one, let me show you a couple different ways I could approach this problem. One, I could just say, well, this is a product of like bases. And when I have a product of like bases, I add the exponents. So this will be r to the negative 8/9 plus positive 17/9 is positive 9/9, which is r to the first. It's probably a step I wouldn't show on my paper because r to the first is just r. The other thing we could do, we could interpret this negative exponent. we could say, okay, r to the 17/9 stays here in the numerator where he is. And this r to the negative 8/9 becomes r to the positive 8/9 in the denominator. Now we have a quotient of like bases where we subtract the exponents, or we like to say how many are left and where. If we have 17/9 of them in the top and 8/9 of them in the bottom, how many are left and where? 9/9 of them in the top. So as it was in chapter 4, many of these problems will have many ways to go about them. You do what you consider to be the slickest. Number 70. A few different ways to start this problem. I think I will start simply by dealing with that negative exponent, taking him across the fraction bar. Z to the positive 3/4 stays where he is. Z to the positive 5/4 stays where he is. Z to the negative 2 in the bottom becomes Z to the positive 2 in the top. Now in this big numerator, let's deal with this product of like bases. Product of like bases, you add the exponents. To add these exponents, I need a common denominator. Rewrite this 2 as so many fourths. 2 is how many fourths? 2 is 8/4. So, product of like bases, add the exponents. That will give me a Z to the 11/4. And now we finish on this quotient of like bases, where we say how many are left and where. There are 11/4 of them in the top, 5/4 in the bottom. How many are left and where when I'm done canceling? Well, that's going to leave me a Z to the 6/4 in the top. Nothing in the bottom, so it'd be over 1, but we don't write over 1. That little fraction does need reduced, and so finally we get Z to the 3/2. Let's have a go at number 72. The only real way to start this problem is by removing the parentheses there in the top. We'll do that by distributing this power over this product. That'll give us r to the 1/5 to the 15. Power to a power, you multiply the powers. R to the 1/5 times 15 is 3. S to the, again, power to a power, you multiply the powers. 2/3 times 15. You ready to cross cancel with me on the fly? 15 divided by 3 is 5, times 2 is 10. If you don't like that, come over here to the side and work that out. It's better to put in an extra step and get it right than to try to do too much at once and miss the problem. In our denominator, we still have this r squared. So the only thing left to do now is deal with my r's. There are 3 of them in the top, 2 in the bottom. How many are left and where when I'm done canceling? That will leave me an r in the top, along with my s to the 10th. Nothing in the bottom, so it's over 1, and we don't write over 1. Number 86. Now before we work number 86, I want to work a companion problem to show you just how straightforward this really is. The only thing that slows us down is we have those fractions for exponents. If this were r to the 3rd times the quantity r to the 5th plus r to the 4th, you know what to do with that to simplify. We'll drop the parentheses by distributing. r to the third times r to the fifth. Product of like bases, add the exponents. R to the eighth. Likewise, we have plus r to the seventh. That's all there is to it. If I were to show a cloud step here, which will not actually be a cloud step in the problem we're going to work, it's going to be one that we actually need to see because of the fractions, I would show that distributing this r to the third looks like this. R to the third times r to the fifth, and plus r to the third times r to the fourth. My products of like bases, I added the exponents to get my final answer. So understanding how this problem works, we're going to do exactly the same in the given problem. We're going to start by distributing this r to the 3/5 to each of the two terms in the parentheses. And I don't think of this as a cloud step this time. This is one of those steps I want to see because I don't want to make a silly mistake trying to do too much at once. We're going to have to add those exponents. But I don't want to go adding those exponents just in my head. I want to see my common denominator here in a minute. And then distributing to the second term, we've got our r to the 3/5 times that r to the 3/4. To simplify this first term, like we said, product of like bases, we add the exponents. For that, we'll need a common denominator. Least common here is 10. So this becomes r to the 6/10 times r to the 1/2 becomes 5/10. In my second term, product of like bases, add the exponents. Least common denominator here is 20. Multiplying top and bottom by 4, that's going to give me r to the 12/20. Here, top and bottom by 5 will give me r to the 15/20. Back to my first term. Product of like bases, add the exponents. I'm ready to do that now that I have a common denominator for my little fractions. That'll be r to the 11/10 and plus r to the 27/20. Neither of my little fractions can be reduced. Those are unlike terms, and so we're done. All right, in this last little bit of the homework set, we've got some problems that we're just going to have to think about. These are thinking problems. Here's what I have. Here's what I want to get. Now, how do I get there? Number 92. Now, her instructions, once again, are leading. I will not provide you with leading instructions. She says write each radical as an exponential and then simplify. Leave answers in exponential form. Assume all variables represent positive numbers. I'm not going to remind you that you can write these radicals as exponentials. I'm going to say simplify. And you're going to say, how in the world am I going to do that? And you're going to have to remember that one of the tools you have now is the ability to change radical form to exponential form. And so here we go. The sixth root of y to the 5th is the same as y raised to the 5/6 power. Your little powers are your little numerators. Your little indices are your little denominators. And times the cube root of y squared in exponential form is y to the 2/3. I now see that this is just a product of like bases. A product of like bases, I'll add these exponents. I'll rewrite this 2/3 as 4/6 to give me a common denominator. Adding those exponents, we get y to the 9/6, and reducing that fraction, y to the 3/2. Now, she did say, leave your answer in exponential form. If I gave you this problem, I'm just as likely to say, write your answer in radical form. So pay attention. If you're not asked for either, then it's your choice. And I would just leave it the first way I come to a simplified answer. But if you're asked to write your answer in radical form here, of course, that's an easy task. This is my little denominators are 2, so that's a square root. And my little numerator, that's the power. That'll be a y cubed in my radicand. If you were asked for radical form. But she wants us to leave our answers in exponential form. Number 94. Simplify. There's actually another way to go about doing this problem because the indices on my radicals are the same. We'll talk about that in a future section. For now, let's go with her suggestion and just work this by changing all of my radicals over to exponentials. In the top, k to the 5/3. In the bottom, k to the 7/3. This is now a quotient of like bases, so I will ask how many are left and where. There are 5/3 of them in the top, 7/3 in the bottom. How many are left and where? 2/3 factors of k remain in the bottom. Nothing remains in the top but that residual factor of 1. Number 96. Simplify. One way to go about doing that is to change things over to exponential form. And so, writing this first radical as an exponential, what's the original radicand? The xz. So what is my base going to be? The xz. Note the parentheses. That whole thing is the radicand, so that whole thing has to be the base. The base of what exponent? A cube root is a 1/3 power. And times square root of z, of course, is z to the 1/2. Now we keep cranking this out with our rules of exponents. Drop the parentheses by distributing that 1/3. X to the 1/3, z to the 1/3. And times this z to the 1/2 here at the end. I have a product of like bases in my z's, and so I'll need a common denominator to be able to add those exponents. This becomes z to the 2/6 and z to the 3/6, a total of z to the 5/6. She said leave your answer in exponential form, and so there it is. Number 98. I like 98. It's another good problem. It's going to be a very colorful problem. It's a fun problem, I think. She wants me to find and simplify the cube root of the square root of k. Change this over to exponential form. The radicand is that k, so it becomes the base. Now what's happening to that k? First, it's having its square root taken, which is the same as raising it to the 1/2 power. And then what happens? Then that result is having its cube root taken, which is the same as raising this whole thing to the 1/3 power. Take a moment and make sure you understand how we change that over to exponential form. Now we're left with just what? Power to a power. Power to a power, you multiply those powers. This will be k to the 1/2 times 1/3 is 1/6. If I were to ask you to write that back in radical form, of course you'd have the 6th root of k. So that's one of those problems that looks a little mean, but really, it's not bad at all. Alright guys, that's our look at 10.2 I'll let you head on over to the homework.